Today we are going to learn about Bayesian inference, understanding prior distributions. We will explore how to choose and use prior distributions in Bayesian analysis, focusing on selecting appropriate priors based on data context and field-specific considerations. Welcome to our exploration of Bayesian inference, specifically focusing on prior distributions. Prior distributions play a crucial role in Bayesian analysis by incorporating existing knowledge and assumptions into the analysis. This, in turn, significantly impacts the results. In this video, we will delve into how to select and use prior distributions effectively. By understanding prior distributions, you'll learn how to integrate domain knowledge into your statistical models, enhancing the validity and reliability of your results. We will cover a range of topics including types of priors, their impact on posterior results, and practical examples from various fields. Let's get started.
Prior distributions are a fundamental component of Bayesian inference. They represent our beliefs about a parameter before observing any data. In the Bayesian framework, they serve as a foundation by integrating existing knowledge and assumptions into the analysis. This initial belief is then updated with new information to form the posterior distribution. By incorporating prior distributions, we can tailor our models to reflect domain expertise or empirical evidence, enhancing the contextual relevance of the analysis. A well-chosen prior can guide the analysis towards more reasonable results, especially when data is scarce or noisy. Understanding how to define and apply priors is essential for effective Bayesian modeling.
In Bayesian inference, priors can be categorized into two main types: informative and non-informative. Informative priors bring in specific knowledge or strong beliefs about a parameter based on previous studies or expert opinion. They are used when we have substantial prior knowledge about the parameter of interest. On the other hand, non-informative priors, or vague priors, are used when little is known about the parameter. They aim to exert minimal influence on the posterior distribution, letting the data speak for itself. The choice between informative and non-informative priors depends on the context of the analysis and the amount of pre-existing information available. Selecting the appropriate type of prior is crucial as it influences the robustness and credibility of the Bayesian model.
Several prior distributions are commonly used in Bayesian analysis, each with distinct characteristics and applications. The Gaussian distribution, also known as the normal distribution, is popular due to its mathematical convenience and ability to represent a wide range of phenomena. It's particularly useful when the parameter of interest is believed to follow a bell-shaped curve. The uniform distribution, on the other hand, is used when all outcomes are considered equally likely within a specified range. It's often used as a non-informative prior when there's no strong belief about the parameter value. Other common priors include the beta distribution for probabilities and the exponential distribution for time-to-event data. The choice of prior distribution should align with the nature of the parameter and the specific context of the analysis.
The choice of prior distribution has a significant impact on the posterior results in Bayesian analysis. The posterior distribution is formed by updating the prior with the likelihood of the observed data. This means that both the data and the prior contribute to the final inference. A well-chosen prior can guide the analysis and improve the robustness of the results, especially when data is limited or uncertain. However, if the prior is too strong or misaligned with the data, it can unduly influence the outcome, leading to biased or misleading conclusions. Therefore, it's crucial to balance the influence of the prior and the data, ensuring that the analysis remains objective and credible. Understanding the impact of priors on posterior results is essential for effective Bayesian modeling. Selecting appropriate priors requires a deep understanding of the domain in which the analysis is conducted. Expert knowledge and empirical evidence can be invaluable in guiding the choice of priors, ensuring that they reflect the realities of the field. For example, in medical research, prior distributions might be informed by previous clinical studies or expert opinions on disease prevalence. In finance, historical market data and economic theories can shape the priors. By integrating domain knowledge, we can enhance the contextual relevance of the Bayesian model, making it more robust and applicable to real-world scenarios. However, it's important to remain objective and avoid introducing biases through overly subjective priors. Striking the right balance between domain expertise and statistical rigor is key to successful Bayesian analysis.
Prior sensitivity analysis is a crucial step in Bayesian modeling. It involves assessing how sensitive the posterior results are to the choice of prior distribution. By testing different priors, we can evaluate the robustness and credibility of the model. If the results vary significantly with different priors, it may indicate that the model is overly reliant on the prior information, potentially undermining its objectivity. Conducting sensitivity analysis allows us to identify and address any vulnerabilities in the model, ensuring that the results are reliable and trustworthy. It's an essential practice for maintaining the integrity of Bayesian inference and avoiding misleading conclusions.
Poor prior selection can undermine the credibility and objectivity of Bayesian inference. Misaligned priors can introduce bias, leading to skewed or inaccurate results. This is particularly problematic when the prior is too strong or not reflective of the true parameter values. Common mistakes include using overly subjective priors, ignoring domain knowledge, and failing to conduct sensitivity analysis. These pitfalls can compromise the validity of the analysis, making it difficult to draw meaningful conclusions. To avoid these issues, it's essential to carefully consider the choice of priors, ensuring that they are well aligned with the data and the context of the analysis. By doing so, we can enhance the reliability and integrity of Bayesian modeling. Understanding how to select appropriate priors is best illustrated through practical examples from various fields. In medical research, prior distributions might be informed by previous clinical studies or expert opinions on disease prevalence. For instance, in a study on a new drug, priors can be derived from earlier trials or similar treatments. In finance, historical market data and economic theories can shape the priors, helping to model stock returns or economic indicators. Environmental science, with its complex systems and uncertainty, often relies on empirical data and expert knowledge to inform priors. These real-world applications demonstrate the importance of tailoring priors to the specific context of the analysis, leveraging domain expertise to enhance the relevance and robustness of Bayesian models. By learning from these examples, we can improve our understanding of prior selection and its impact on Bayesian inference. In conclusion, prior distributions are a critical component of Bayesian inference, shaping the analysis by incorporating existing knowledge and assumptions. Understanding the role and impact of priors enables us to select them carefully, ensuring that they align with the data and the context of the analysis. We have explored the types of priors, their influence on posterior results, and the importance of domain knowledge in guiding prior selection. By conducting sensitivity analysis and avoiding common pitfalls, we can enhance the reliability and credibility of Bayesian models. Thank you for joining us in this exploration of prior distributions in Bayesian inference. We hope this video has provided you with valuable insights and practical knowledge for your future analyses.